Thank you everybody for coming. Today we have the honor of having Professor Rajeeva Karandikar, Director of the Chennai Mathematical Institute, to talk to us about some issue on sample size and its impact on selection of on election matters. And although Professor Karandikar does not need any introduction, let me give you a brief introduction of him anyway. He has did his PhD from the Indian Statistical Institute in 1981, and then he went on to do his postdoctoral research at the University of North Carolina, Chapel Hill. He came back to ISI as a professor, became a full professor. He got the SS Bhatnagar Award, and he did various other things. He was editor of Sankhya, he was the associate editor of Annals of Probability and various other things. He's a member and fellow of different national academies of sciences in India, and he's been well known in the area of psychology for now 2 decades, right? So 2 decades, and so he needs no introduction in that regard. He has also written extensively about probability and statistics and related matter. He has half a dozen books and 70-odd papers in scientific journals, and thousands of citations of his journals. So he's a very well-known academic as well as a very seasoned practical practitioner of election-related things.
Thank you for the introduction, and today I'm going to just focus on one issue which bothers people whenever I give a talk on elections and predictions, and in this short talk that is what I aim to do, which is how can a sample of say 50,000 respondents tell us anything about the national mood in a country like India, where at least 55 crore or 550 million voters voted 5 years ago. In the coming election, even more expected to go up by about 10%. So, the sample is less than 0.01% of the population. So, common people have this perception that how can such a tiny fraction tell us anything about what is likely to happen or the mood of the country. So, I'm going to do an experiment in front of you. So here is a box. The box has slips of paper, 100 of them. It can be audited by somebody in the audience later. There are 100 of them, and they are all identical. If the camera can see this, they are all identical, folded, and each one has a letter written on it. It is either a A or a B. Okay? I'm going to do two things. I'm going to tell you, and you is rightly so, that there are exactly 2 possibilities. 99 of them have an A and one has a B, or 99 of them have a B and one has an A. These are the only 2 possibilities. Having said that, now I am shaking this up and will draw one at random, and I'll open it out and read it out to you and see what it is. So it says an A. Perhaps the camera can't see it, but I'm saying that it's an A. Now, this is what we have observed. Okay? We believe the story that I told you, that 99 is one letter, 1 is the other letter, and we shook it up, drew out 1, and there is that, opened it out and saw that it's an A. Of course, we have to make a prediction or guess as to which of the 2 scenarios is in vogue here. Is it 99A and 1B or 1A and 99B? Okay? Of course, both are possible. It's possible that it is the second scenario, and I happen to pick out that 1A and open it up. That's possible. I have done this experiment at multiple locations and asked the audience to make a guess. And depending on who the audience is, sometimes there is a response sometimes there is none, sometimes there are many people eager to give a response. So whenever there is a response, it is always the first one and not the second. Never has anyone given the second response. Now, different people go through different things in their mind, and somebody would say that what is there to guess? It is common sense. That is what we do all the time. There are two scenarios, we weigh in the possibility of the observation under the two scenarios and make a judgment. Now, what goes on behind, at least not everybody's mind, but some folks' mind, we can capture through the following. Chance that the randomly chosen slip as an A, okay, under the scenario 1 has 99% probability. Because scenario 1, remember, was 99A, 1B, 100 cases, 99 favorable, 1 not favorable, so 99%. And under scenario B, or scenario 2, the chances are just 1%. Of course, the other possibility is there, but we have observed this one, so let's not even go to the second one. And when a given observation has two possible explanations, and under one of them it is highly more likely than in the other, we tend to go with the one which is under which the observation is highly likely. That is what people do in common sense in day-to-day life. Whenever we have to make decisions under uncertainty, that is what we do. And of course, statistical theory just captures common sense in simple situations, and we then extrapolate it to get to more complicated scenarios where common sense may not shed any light. Okay? So, this much, if you accept that in view of this calculation, having observed 1A, if we have to choose between scenario 1 and scenario 2, we choose scenario 1. That's it. And this is all that is needed to convince you that indeed a sample of size 50,000 can give us insights in a country like India too. And that's what I will do in the rest of it. Okay, so let's continue with this. Okay, let me capture this as follows. That if we take the strategy that the observed letter is the dominant letter, okay, one can compute that the accuracy of this strategy is 99%. I'm not getting into this calculation. Accuracy has to be defined and computed, but let us keep it at an intuitive level. Okay, and now let's make a variation. Instead of telling that there are 99 and 1, this box actually has 99 and 1, but now assume I am a mathematician, so I can start assume and then say anything, right? So assume that I have another box which has, I tell you now that there are two scenarios, 95A, 5B, 5A, 1B. Okay? So, we still draw 1. If we draw 1, the common sense, the strategy would still be to pick the scenario, the observed letter is the dominant letter. Except that this time, the two scenarios, earlier time it was 99, 1, the ratio was 99, now it is 95 and 5 and the ratio will be 90, which is much less than 99. So, maybe it will not be an emphatic scenario 1 as the answer. If at all we have to guess, we will say scenario 1. That's what happens. But, now let's do a variation. Instead of drawing 1, and then put it back, shake it up again, draw another, read it out, put it back again, shake it up, draw another 3. If I draw 2, then it can be a tie and we are clueless as to what to guess. But therefore, if we draw 3, then we know that either all 3 will be the same or there will be 2 of one and 1 of the other. So, in any case, either A or B will be majority out of 3. That's why odd number. And here is a calculation that assumes that the majority of slips at the A, then the chance of this observation in the scenario 1, you can simply say that all 3 can be A or 2A and 1B, and the calculation is from class 10 calculation, and it is actually above 99%. So 99.9927. And under scenario 2, it is the 1 minus of this, so 0.0073. So in a sense, though the split is 95-5, by repeating the observations 3 times, or repeating the experiment 3 times, we have raised the level of confidence to as if it was a 99-1 split. And now we are back in the game. What this calculation tells us is that if you once again have a strategy that the dominant letter, namely the letter which has majority out of 3, is dominant letter in the box. That means that is what is present in 95% of the cases. The accuracy of this strategy is over 99%. So this leaves a possibility. Those with mathematical mind can see that even if it was 90-10, maybe it will not be 3, but maybe it will be 12, maybe it will be 20. By the time you get 99% accuracy for the dominant letter in n draws to be the dominant letter in the box, and we should take n to be odd so that we never face with the case that there is a tie. Alright? So, this tells us a possibility that if the gap becomes narrower and narrower, you have to draw more number of draws. How many draws we need? We can do a simple calculation. We'll come to that. But let us now address the main issue about what has the population size to do with it. So here my list size are 3 draws. So 3 is the sample size and 100 is the population size, total number of slips in my box. Okay. So now let's just vary and say instead of 100, if there were 1000, what would happen? So let's consider that there are actually 1000 slips. Still the split is as it was before, 95%, 5%. Once again we draw 3. Now, the accuracy of the strategy that the dominant letter in 3 draws is the dominant letter in the box, this time is given by this expression. So each factor in each term from our previous calculation, whatever was 95 becomes 950, because this time out of 1000 we have 950 of the dominant one, and what was 5 becomes 50. So the numerator, every factor in every term gets multiplied by 10. So each term gets multiplied by 1000. Same denominator here. And therefore this 1000 cancels and our ratio is back to 0.9927. So this calculation is the crux which says that whether we had 100 slips or 1000 slips, if the split is 95-5 and we draw 3, the strategy of going with the dominant one in your sample, accuracy is 99%, over 99%. And now you can see that instead of 10, I multiplied everything by 100, 1000, million, doesn't matter. That means whether the total number of slips is 1000, million, 100, a billion, doesn't matter. Even if you have billion slips, 95-5 split, draw 3, go with it. So this is already answering the question I posed in my title, that it is the sample size, namely 3 which is important, and now not whether it is 100, 1000 or a million or a billion. Okay? And this is a simple calculation which tells you. And all it needs is that the probability is number of favorable cases divided by the total number of cases. It has not used any complicated maths, it has not used any complicated approximations, nothing. Okay? So, dominant letter in 3 draws is the dominant letter in the box. If the box has 95-5 split, no matter whatever be the number of slips, that means no matter what be the population size, if it is 95-5, just drawing 3 randomly will tell us who is most likely the winner, who is most likely the 95 Alright. So, this explains the somewhat counterintuitive fact that accuracy of decision based on sampling depends on the sample size and not on the sampling fraction. And I have chosen one definition of accuracy, somebody else can have another notion of accuracy. Whichever notion we work with, this will remain true. Okay. Counterintuitive but true. So, of course, one question somebody may have is, okay, 95-5 is an extreme case. We really would not be needing in the election context. If it is a split is 95-5 between 2 candidates, we don't need sampling. We all would know as to who is popular and who is extremely unpopular, right? So, we should look at situations where it is closer. The split is not 95-5 but closer. What happens? And okay, before that, in practice, one does not put back the slips drawn once in the box again before and shake it up and draw again. Because imagine I am doing an opinion poll and I pick one person at random and he or she gives the answer, and my fifth draw is again the same person. I go again and say, "Arey, I have already answered." And we say, "But you appeared twice in my sample." And that will make me look stupid. So that is never done. And therefore, what we do is actually sampling without replacement. After drawing, let's say 5 draws, the sixth draw is a random draw from whatever is remaining, excluding the first 5. Okay? Actually, the accuracy improves a little. Mathematically, one can show that it only improves for small sample size. So, for 100 this time, so earlier I had 95, 95, 95, now it becomes 95, 94, 93, and then 5, 95, 94. And I made a mistake, denominator should have been 100, 99, 98. It's a mistake. So, but the ratio I have computed correctly, I just did not put in the right numbers in the slide. Okay, so the accuracy only improves somewhat. 0.9927 became 994. That's all that happens. And what can be shown is that whatever be the number of slips, the accuracy in this case, 95 slip, 3 draws go with the majority, remains at least 0.9927. So what we got as the answer from sampling with replacement is an upper bound, and in sampling without replacement, we improve things a bit. The improvement is significant only when the sample is a significant proportion of the population. As this goes down, which is typically the case, then the answers are the same with and without replacement. So, alright. Now, let's go to election scenario. And let's take a constituency with say 10 lakh, that is 1 million voters. And simple situation, exactly 2 voters, A and B. And suppose one of them is 52%, suppose. So now I have come down from 95 split to 50 to 48. What happens in this case? Well, let's say if I draw all possible lists of size 4001. Okay. Now, out of 1 million total voters drawing these many number of lists, even if I have to store them on the computer, it will eat up a huge amount of memory. But we are doing a mental exercise. Let's say we draw all possible lists of 4001 size, and each list is labeled as A or B depending upon what is the opinion of the majority of the voters appearing on that list. So, because my list size is odd, each of them will have one of them will be dominant out of 4001. At least one will have 2001 supporters, and I label it that way. Okay. Now the question is, what is the proportion of lists which will show the dominant person as the labeled as the dominant person? And this time, a simple calculation, counting argument that at least 99.4% of the slips will have the label of the candidate who has majority support in the population. So the calculation is simple, the argument is simple, actual calculation doing by hand is impossible, but today one can do it with the software. In the olden days, one had to use approximations, Sterling's approximations and so on, and then compute this approximately. Today we can do an exact calculation and get that it is 99.4. So, what this says is that even in a constituency with 1 million voters, 10 lakh voters, and a fairly close election, 50 to 48, remember, is fairly close. It can be closer, but if it is 50 to 48, a random draw of 4001 gives us complete insight into who is likely to win. Of course, one has to do random sampling. If you do shortcuts there, then all bets are off. That goes without saying. The whole argument is based on all draws or all lists are equally likely short circuit that, then bets are off. Then one has to examine what is the sampling mechanism, and then for that sampling mechanism one has to do these calculations. But the purpose here was to just show that if we do perfect random sampling, today it is possible. In old days maybe it was tough, but today it is possible. In each constituency one can get a list of all polling booths from the election commission, and for each polling booth we can get the list of all voters. So it is possible to actually randomly generate a list of 4001 and go and door to door and get their opinion, and simply whoever is the majority out of this 4001, close your eyes and say so and so is the winner. That's it. 99% accuracy. And to stress again, whether it is a 1 million or 10 million, the 4001 requirements remains frozen. And if 1 million becomes 100,000, it still remains 4001. And that is something which people are not so easy to accept, but the attempt in this was to convince you, and the whole crux of the argument is between, for this, what I showed here was the 95-5 split and 100,000. That is the crux of calculation, to convince you that it is sample size which matters and not sampling fraction. So the sampling fraction, people mean the sample size divided by the population size. And typically, whenever one makes any sample-based prediction, the first thing people jump is they compute sampling fraction and say, that is so little, how can you say anything? So, here is the answer. Thank you.
Thank you.